Anyone who has taken cinema studies courses knows that one of the obsessions of theorists and philosophers of cinema is to talk about what they call the gaze, which means the look. And there are countless theoretical works which talk about vision in cinema, which talk about what it means to look at cinema, which talks about what the look does in cinema. The group of theorists speaking about cinema and vision are talking about, when they use the word vision, has nothing to do with what these three guys are talking about when they use the word vision. And I found that very perplexing because supposedly we all know that vision is not something abstract, that actually depends on the eye. It's actually a physiological phenomenon, and it is a relationship to the real world, whatever you call that real world. So it seemed to me to be something that is profoundly overlooked. And recently, actually, in the last couple of years, I'm not the first one to think about the fact that this has been overlooked. And there have been theorists who have been trying to breach the divide between science and theory when talking about what happens in cinema. If I give you a brief overview, a very brief overview about how vision and the gaze have been discussed in cinema studies, I would start with Bazin. And here's my brief overview right in front of you. Okay, so Bazin was one of the leading French theorists of what makes cinema such an astounding medium. And for him, what makes cinema astounding is that it is transparent reality. That what you film is what you see. It's real. And that no other medium, not even photography, can capture real life exactly as it is seen. And one obsession with the eye is the idea that the camera is an eye. It's kind of an eye because it moves around like an eye. In fact, in many films, it kind of imitates that feeling of being an eye with its tilts and its movements and the way it goes, zooms in close or goes back. And the theoretical and metaphor for the eye in cinema philosophy is that the eye is power. The eye is associated with having power over the object or with other people. And that idea of the eye having power is best substantiated by the work of Foucault, Michel Foucault, who in his Discipline and Punish wrote about Jeremy Bentham's 18th century prison. And the 18th century prison that Bentham thought of or created or imagined, he thought would be the ideal prison because it would be a prison that was round, and in this round prison there would be a central observatory, and in each of the cells there would be a prisoner who would know that at any moment that central observer could see that person in the cell and observe what he was doing. Well, the brilliance of this prison is that people became so self-conscious about being watched that after a while you could eliminate the man in that central observatory, and you didn't even have to have someone looking at you. You will internalize the idea of an eye watching you. And this is Foucault's metaphor for modern society. He thinks that everyone has internalized an eye watching us, which is how power works on us without us being aware of it. Well, why am I mentioning Foucault in this metaphor of the eye in this class is because if you look at cinema studies when they talk about the gaze, they talk about the camera as having power over its objects. And it goes one step further. One of the most popular theories about the camera and the eye in the 1970s and 80s came from feminist study, which said that the camera is always identified with the male eye, and that the male eye in our society is metaphorically the powerful eye that captures, controls its object, which is female. And this theory was supported by the fact that most Hollywood film, well, not most Hollywood film, but a great majority of Hollywood film will have the main character be a hero, like Jimmy Stewart, who follows around a mysterious woman, and the camera follows this mysterious woman, and the mysterious woman is the object of desire. And this theory suggested that most Hollywood cinema is based on the idea of the camera being a masculine eye that searches out its subject. Along the same lines, the eye in cinema theory has been associated with sexual desire, that the eye is the locus for desire, And to look at someone means to have desire for someone. And looking, desiring, wanting, and wanting control over somebody, are synonymous. And that's what movies replicate when you watch them. You actually are identifying with a camera, which is a vehicle of desire, like the eye, that is going to control some subject. This idea of the eye as male, as having sexual desire, as being connected to the Foucaultian idea of power, obviously, to me, has very little to do with what the vision scientists tell us that eyes do. Unless the eye naturally, by looking, has some connection with the body feeling empowered or with sexual desire. I have never read anything like that. But I just want to bring this up to show you that there is a split between the eye as metaphor, the eye as considered in Western culture, and the eye as it actually works. And there's a long history of the gaze. In art studies, it's John Berger who talks about the way eyes look in paintings, and he's also a very big figure in cinema studies as well. But switching to the relation of cinema with actual seeing, which is the subject of today's workshop, I wanted to point out that reading their works has led me to a series of questions about how could you apply these issues of vision that they bring up in their work, which is very difficult for non-scientists to read, and we have all really done a good job in trying to do so. How could it relate to cinema? And I'm just bringing up some suggestions very rapidly here, so that at the end of the class, if anybody wants to pick up on them, they're free to, because it would be nice to see if that goes anywhere. First, one connection can be from Patrick Cavanagh's work, he looks at how paintings, that artists are naive scientists in that they implicitly use conventions that have been developed for thousands of years that rely on an elementary physics of the eye. And so I was wondering whether such conventions are actually applicable in cinema, whether the fact that cinema is seen as a continuous reality, whether some of the conventions of continuity editing might be based in an elementary physics of the eye, that they're not just by accident. Another thing I find a pleasure of movies, especially contemporary movies, is trying to resolve ambiguity. A lot of films will have a shot which we don't understand what it is until we see the next shot. And that idea of what is it, how is our brain supposed to interpret what we just saw, is one of the pleasures in watching cinema. So that we will be constantly choosing between different ambiguous notions of what it could be. Okay, see, there he is looking, the typical shot of looking, here's the woman he's looking at, and now the next shots are going to be him following her with a gaze. This is considered the standard scene of what Lauren Mulvey calls the male gaze looking for the female. But what I find interesting here is while the theory talks about the male gaze looking at the female, conscious of what I read in these three vision scientists' works, am conscious of the fact that really it's about someone entering new spaces. It's basically, he's going to be entering lots of different spaces that have different colors, different textures, different dimensions, and the excitement of the spectator is actually to be led visually through these camera movements into spaces that surprise you with unexpected, for example, color. Because what's interesting also with these films that I didn't mention is that as much as they show the power of the gaze and gaze as knowledge, look at that gaze right there, there's also still the idea that gazing is an illusion and that you can never completely know. Okay, here is the great scene of vision of Clockwork Orange, where Stanley Kubrick, who loves the concept of the gaze as well, as do all cineasts, shows Alex, who is a violent young thug, being brainwashed and turned into a mild-mannered, nauseated young man because he is forced with eye drops to watch movies, and these eye drops will make him have a different physiological reaction to what he sees, and he can't blink. And for Stanley Kubrick, I believe he even stated this in some interviews, this is his impression of the modern world in the way we are manipulated by media and brainwashed to become subjects of this kind of the powers that be. It's kind of a Foucauldian idea of power. Here are the scientists, of which we have 3 today. Okay, Gaspar Noé's Into the Void, which is one of these modern experiments with using the camera in wild ways, in that it's full of ambiguous scenes because the character is dead, so we just basically see the whole film through his dead eyes. You see, we don't know what that is, and then we have to wait until the next shot to see what that is. And this is a lot of play on it leading the spectator into a hallucinogenic sense of vision. And the pleasure of this movie is precisely in its visual techniques, because unless you like the story, which I personally don't, but some people do. And so that ends my little 15-minute overview of vision in cinema in the last 70 years. And now we're going to turn to vision and how it actually works. Will, can you switch those things? And Kevin O'Regan, the director of the CNRS Perception Lab, is going to now enlighten us about the real eye.
This is what a vertical eye looks like. Light comes in through the pupil at the front, goes through a lens, and then falls on the back of the eye where there's a thing called the retina, where you have photoreceptors that are like the pixels in a camera, and they pick up the light, and they transmit it via the optic nerve to the brain. But the trouble is that the pixels, the photoreceptors that sense the light, are arranged the wrong way around. Instead of facing towards the light, they're facing away from the light for some peculiar reason to do with the way organisms have evolved. And this means that the wires that are connected to the photoreceptors come in from the back here, and the light has to traverse the wires in order to get to the photoreceptors. And another thing, and unfortunately it doesn't matter too much because the wires here, the axons, are transparent, or fairly transparent, so you can see pretty well, despite the fact that they're lying on the wrong side of the retina. But then the axons come together and they go out of the eye in a cable here, called the optic nerve. And obviously here where the cable is, there can be no photoreceptors. So there's a part of the eye here, right at the middle of the back of the eye, where there are no photoreceptors, and so no pixels, and the eye cannot see anything, in fact. And that's what's called the blind spot. The blind spot, in fact, is so big that it can engulf an orange held at arm's length. If you close one eye, you look straight ahead, there's a place in your visual field where an orange can be held where you will just simply not see. Now, why is it that, despite the fact that there's this big hole in the back of each of our eyes, we don't see a hole in the visual field in front of us? Why do you have to use some special method like this, positioning it very carefully, to actually see that there is a big hole in your vision? So that's, say, one mystery of vision. Another mystery of vision is the fact that the eye moves around all the time. So if you're looking at something, during normal everyday activity, your eye is jumping around at about 3 to 5 times a second. And it makes very, very fast movements. And when it jumps from one position to the next, essentially on the back of the eye, what do you have? Well, you have a smear. And this smear occurs 3 to 5 times a second, all the waking day. And yet you don't see it. Why don't you see it? And the other thing is, of course, when the eye's got the other side of the smear, the eye is in a different position. And so now the image at the back of your eye is in a different position. So why is it that when you move your eyes around, you don't see this image shifting around? If you have a camera and you move it around, you know, your photograph is shifted around. And in fact, you can see what it would look like for the image to shift around in this way. If you close one eye and you push strongly on one side of your eye through the eyelid, then you can perfectly see the movement. And yet, during normal activity, you just don't see this movement which is occurring 3 to 5 times a second all day. Why not? And here's another problem with vision. You know, the eye is a sphere after all. So if you're looking at a straight line, okay, the straight line falls on the retina at the back of the eye, where it traces out something like the equator. But then if you move your eye off the straight line, now the straight line is projected at a different point on the back of your eye, and it projects another kind of arc at the back of your eye. So if you flatten out the retina now, you've got the straight line you were looking at to begin with has now become a curved line. And yet when you look at straight lines and move your eyes around near them, you don't see them curving and becoming unstraight. Why is that? In fact, it's even worse than that. Because this is the retina, say, I've schematized the retina, and the pixels at the back of your retina, the photoreceptors that sample the information, that sample the image that impacts on the back of your eye, these pixels, these photoreceptors sample the information there in a non-uniform way. So at the center of the retina, the photoreceptors are very small. I've symbolized them here as little colored triangles. But as you go into peripheral vision, the photoreceptors become much bigger. So in the brain, in the cortex, where the information is projected, arrives, in fact, at the center of the line, you have a lot of information. But at the edges of the line, you don't have very much information. And in peripheral vision, a line here would give you very little information. So how is it that in the brain, how is it that you see two lines as being straight and parallel and of equal thickness all along their length, when in fact in the brain you have some kind of very distorted representation of this?
If you have the answers, you can try.
There are no answers. Another question concerns color. You know, you have the impression when you look out in front of you that you can see a wonderful, colorful scene, okay? But in fact, the receptors that measure color in the eye, being sensitive to color in the eye, as I said here, are represented by these photoreceptors that are sensitive to two different bands of wavelengths of colored light. But as you move into peripheral vision, these color-sensitive sensors are replaced by sensors that are not sensitive to different colors. And they're called rods. These are called cones and these are called rods. And in peripheral vision, you essentially only have rods, which means that in peripheral vision, you just don't see color. In fact, colored vision is so bad in peripheral vision that if you look at somebody's nose, for example, this is you looking at somebody's nose, and they hold some colored pencils out at arm's length, and they bring the colored pencils in towards their ear. If you keep looking at the nose, you will see you are unable to say what the colors of the colored pencils are. So even very close to the center of vision, color vision is very, very bad. And despite that fact, we have the impression of seeing color everywhere. Why is that? So I have a theory that I have written up in my book, which I wrote. This is just a big advertisement for my book. This is my book, which has just come out with Oxford University Press. It's about consciousness and vision. The title of the book is Why Red Doesn't Sound Like a Bell. And in this theory, I compare vision to touch. The thing is that, in fact, if you are a blind person and you touch the table here, you feel the table as being continuous. There are no holes in the table, right? And yet there are holes in your finger, between your fingers. So if you were thinking about vision, you know there's a hole in your retina. You don't see a hole in the visual field. If you're thinking about touch, there's holes between your fingers. So why don't you feel holes in the table? That's curious, because thinking about vision, we're really bothered by this problem. Whereas thinking about touch, we're not so bothered. Why not? Because we all know that touch is an exploratory sense. We move our hands around to explore the table. And the fact that there are holes between my fingers doesn't make any difference whatsoever. I still know that the table is smooth and has no holes, because I know that if I move my hand a little bit to the left or to the right, it will still be there. There won't be a hole in it. So essentially in my book and in my theory about vision, What I suggest is that vision is more to do with sampling information with your eye as though it was a giant hand that you sample the outside world with, in the same way as a blind person samples the table when he touches it. And if you think about vision in that way, all the problems I've been telling you about evaporate. And you can understand that vision is an exploratory sense. There is no internal movie cinema which is going on inside your head, which has to be, which have these defects that I've been telling you about. Because vision always involves you interrogating the outside environment. But what does that mean? It makes a prediction. If vision really involves interrogating the outside world, if vision is not receiving an image inside your head, vision is not like having a cinema projector inside your head. If that's true, if vision is interrogating the outside world, then what you see will be determined by essentially what you're asking at any moment, and not what you are contemplating at that moment. So for example, in a case like this here, you might think the sign here says, the illusion of seeing. Please raise your hand if you see something different from the illusion of seeing. You shut up. Raise your hand. So about half of the people here have not noticed that it says the illusion of seeing. The word of is written twice. Okay? You can look at that for 10 minutes without seeing the second of, because you are expecting the of to be there. And despite the fact that your eye is right on it, you just don't see it, because seeing is not contemplating. Seeing is interrogating the environment with your knowledge. Okay? And in fact, this makes another prediction. It makes a prediction about driving. I'm driving along the road. Okay? I'm going through a railway crossing. I've been driving on that road every day for many, many years. And usually when I go through the railway crossing, there's no train. But today there's a train. The train is going slowly through the railway crossing. And what will happen is that you will just crash into the train. Because even though you are looking straight at the train, you just don't see it. Because you know that there's never a train there. And in fact, if you look on the web, if you do a Google search for train hits car on railway crossing, you will see hundreds of examples in local newspapers of cars hitting trains. You might expect it was the other way around, but it's not. The major cause of accidents at railway crossings is cars hitting trains. And this phenomenon is called looked but failed to see. It is the third most frequent cause of accidents in general in driving, after drunken driving and driving in poor visibility. It's the third greatest cause of driving. The driver is looking straight at the motorcycle who is coming in from the side. He's looking at him. The motorcycle looks at him, sees that the driver is looking at him, and thinks he's okay. But the driver, although he's looking straight at him, just drives into him. And there's an accident. This is the third greatest cause of accidents. And why is this? It's because looking is not seeing. Seeing is interrogating your environment. And it's all to do with attention, of course. Dr. CAVENAGH is a great expert on attention, and he'll no doubt talk more about it. But here is an example typical of what psychologists do when they study attention. They get you to do a task where you have to apply a lot of attention. Here your task is to follow the coin that is moving around underneath the cups. And it's going to be slightly difficult because as the cups move, there are other hands here moving them around. And your job is to see if you can determine where the coin ends up at the end. You have to concentrate a bit because it's sort of complicated.
Can we do it again?
Wait. Some of you may be able to tell me. Okay. Now raise your hand if you saw the green pepper. So 4 or 5 people saw that there was a green pepper.
What green pepper?
But most of you did not see the green pepper, which I will show you, which was right before your eyes, like the motorcyclist, like the train, because you were thinking about something different. You were trying to follow the coin, but the green pepper came right in there, and it was right before your eyes, and you didn't see it.
That's in this version.
And it's again compatible with ambiguous figures like this, where if you look at the tip of the black nose here, you can either see the black face or the white face, but you can't see both. Because seeing is not looking, seeing is extracting and constructing information in front of you, and it is determined by what you expect and what you know previously. And this is also shown by eye movements. If you look at somebody, if you measure the eye movements that somebody will make when they scan a picture, you'll see that the eye kind of moves around. So this is a typical eye movement trajectories for looking at pictures. Now, this is a picture where somebody was looking for something that was going to change in the picture, and their eyes were going around. And you might think that because they were looking for something that was going to change in the picture, that their eyes would move to all over the picture. But this is the first sort of 20 or 30 seconds of scanning, and this is the next minute or so of scanning. What you see is people's eyes just go round in circles. And the reasons people's eyes go round in circles is because what you do when you look at a picture is you are interpreting the picture, and you look at what you look at is determined by how you are interpreting the picture. So obviously this person was thinking to himself, well, this is a man and a woman having dinner, and the eyes just kept doing the same thing over and over again. This is another demonstration of how attention and how vision is determined by what you know. Now, usually when you look at a visual scene, you have the impression of seeing everything in wonderful technicolor and splendor in front of you. And what I'm saying is that that is actually an illusion. You do not see everything in front of you. You just think you see everything in front of you. And one of the reasons you think you see everything is because you think you know already what's out there. But there's another reason that explains why you think you see everything. And the reason why you think you see everything, or that reason is that if anything should change in the picture or in the scene, like here, it pops out. You see it. So even though maybe if I had asked you, if I had shown you this picture and I said, is there a bag on the table? I could have got you to look at the picture and then close your eyes, and I would have said, is there a bag on the table? You probably simply didn't know. But still you think you saw it, because if the bag should suddenly appear or disappear, then you would see it. Okay? So really part of the illusion of seeing everything comes from your implicit faith that if anything should change, you should see it. So that gives you the incorrect impression that you are seeing everything, because you have tabs on everything. You think that you're seeing it, because if it should disappear or appear, you would see it. So there's a way of showing that I'm right, and that is by making the change in such a way that the usual mechanisms in the brain that alert you to the change do not function. So this is a picture where I'm going to make a big change in the picture, enormous change, but I'm going to mask the change with an even bigger change. So this is the picture, that's the even bigger change, and that's a new picture. This is a completely different picture from the first one. And you probably don't see the difference. There's about a third or a quarter of the picture which is changed between this and this. So raise your hand when you see the difference. Aha, well you're pretty good. It's the reflection in the lake. See?
Oh.
This phenomenon is called change blindness, and there's many, many different ways of showing it. Here's another example where instead of putting a big change, I put what I call mud splashes. There's one picture, and here's a different picture. And those were mud splashes, like splashes on the window screen when you're driving a car. This is a different picture. So you probably have not noticed that it is the dotted line in the street there that is becoming continuous. And it's in full view, so it's... And this is another example by Simons and Levin again. Brilliant. So Dan Levin goes up to somebody in the street and asks him where the library is. And Dan Levin is going to be magically transformed into Dan Simons right before the eyes of the passerby. He just keeps talking to him. And the man is completely unaware of the change.
Vision comes at a cost. To have binocular vision, of course, you have two eyes, more is pointing towards the same direction, so in the front, so that you need some kind of overlapping vision between the left eye's view and the right eye's view. That comes at a cost because that means that you are losing vision from the side. If you were a duck, for instance, you might be better at detecting some predators or some prey coming from the side, and we have lost this ability. So this is a cost for some kind of benefit, and we have to look for that particular benefit. I'm not going to bother you with the real kind of experiments that we do, but maybe one central problem in binocular or 3D vision in the lab is not really maybe interesting to you, but it's looking at the very basic problem which is called the correspondence problem, which is to try to identify which feature in one eye will match the features in the other eye. And this might look like a trivial problem, but in fact it's a very challenging computational problem. The visual system has to try to find features in one image and match that to the other's eye image. And it's a computationally very challenging problem. I'm going to skip that. Skip the kind of stimuli that are being used for that purpose. The one thing that is quite interesting in stereopsis is that it can have drastic effect on other properties of the world. This is an illustration from the work of a previous colleague of Patrick Kahneman. So these are supposed to be images that you diffuse. Sorry? It's yours. Oh, okay, well the next one is not yours. This image is yours. Okay. Well, this is Patrick's work. Where this is the left eye image, this is the right eye image, and this is again the left eye image. And when you are going to fuse, say, the left two images, so left eye, right eye, you might see some kind of illusory square that is floating in front of the background. When you are fusing these other two images, you have a completely different interpretation. Now you see 4 holes, and you look through these 4 holes, and you see a white diamond on a black background. So just the information in the monocular image is just the first step for your final interpretation of the 3D world out there. And this is a similar, but a slightly different author's presentation, where now you, again, same idea, you are going to exchange the image so by the left eye and the right eye. In one interpretation, you are going to see some folded cards that are red on one side and white on the other side. And in another interpretation, if you fuse the images the other way, so exchanging what the left eye is seeing and what the right eye is seeing, you now see 4 frontal parallel white rectangle and some transparent red film in front of it. So again, the image that is impinging on the retina is really just the first step. Your visual system then is doing a lot of processing to extract some material properties of the scene out there. So this is stereopsis, but of course there are a lot of other cues that the visual system is using. There are about 5–10% of the population in the Western world that doesn't have stereopsis. And out of this 5–10%, there's a good half that doesn't know that it doesn't have stereopsis.
Can you define stereopsis?
So stereopsis is the ability to extract 3D from binocular vision. So 3D is not just the result of stereopsis, of binocular vision. There are a lot of other cues, and luckily for us in billboards, in magazines, and in cinema, 2D cinema, you have still a good sense of 3D, even though you have only molecular information. So these are examples of good extraction of 3Dness from just perspective, mostly perspective cues, without any. So stereopsis again is playing with the small disparities between left eye and right eye. Here, in this case, they are none. There are a lot of other cues that the visual system is using. This is maybe more like in a perspective. This is accommodation.
So can I just interrupt? One basic question. Is it true that to see depth, you take information from each eye and put it together? Or if so, what does that mean?
Well, that's binocular vision, and that's stereopsis.
Okay, that is it.
Yes. That's where you take the image from left eye and right eye. You compare the small differences, discrepancies between what the left eye is seeing and what the right eye is seeing. And these small disparities, these small discrepancies between what the left eye and what the right eye are seeing are then converted to some 3D, to some depth information. After resolving the correspondence problem, after resolving what feature in the left eye is matched to the right eye. That is called chromostereopsis. So when I said that stereopsis requires two eyes. It's requiring to have some small disparities between, small discrepancies between what the left eye is seeing and what the right eye is seeing. This is chromostereopsis, and the small disparities. That is one explanation of this phenomenon, that the small disparity between the left eye and the right eye is not coming from different viewing angles, but it's coming from different colors. So here you might see, I don't know if it works, but you might see that this one, the blue is set in front of the red. Behind? Who is seeing the blue in front? Thank you. Who is seeing the blue behind? How does this one? This one works. Yeah, this one. Yeah. Okay. This might come. I don't want to go into the details, but this might come through some. I'm not going to say.
Thank you, Pascal.
This might come from chromatic aberration in the eye. Now you know. Maybe the strongest cue, at least the one that you find almost all across the animal kingdom, is coming from motion cues. And one of these motion cues is illustrated here. You might, some people, you might see some kind of transparent sphere that's rotating, and you might see that this bistable is rotating, say, in one direction or in the other direction. It's a bit like there's some on the web of that with a naked dancer that is rotating on 1 foot. So supposedly, depending on whether you see it rotating one way, you're using left brain, and if you see it rotating the other way, you're using the right brain.
What about at the same time?
This is bullshit. You cannot see it. Can you see it?
Yes.
Switch.
Yeah, it switches, yes, right. Switching is good, but if you see two rotations at the same time, you can't see the Right, so obviously here you have a bit of sense of the depth because you do eventually see some kind of sphere, transparent, just from the motion information. And the motion speed is then translated into some kind of depth. This is an example where motion is used again, but now it's used in such a way that this is just a single image that is rotated in the image plane. And you might perceive like two cones sliding on top of each other. If you see that. Okay. At least somebody's here. Thank you, Patrick.
Two cones doing what?
Sliding, touching on one.
What else could you see?
Well, you could see. Oops, sorry.
You could see Venice?
You could see just. You could see just this, which is just an image. You could see a flat texture with some kind of interesting pattern of non-concentric rings. This more or less. This should look flat, more or less.
Uh-huh.
But if I give it a spin, now it's...
So the movement itself gives it the 3D?
Yes. Right.
But why does movement cue us to 3D?
Well, this is very unclear. But this is an illustration of the kind of very low-level information, small motion information on the retina that your visual system is going then to extract some kind of depth or volume out of a single flat image. Surprisingly, I mean, you are very bad at making judgments about the vertical three-dimensional world from inner perspective. This kind of lines that are converging to vanishing point in the image seem like to give you a very good sense of depth. But if I ask you to judge the orientation about this building relative to your line of sight, you are going to make a very stereotyped but wrong judgment. You overemphasize, you have to overemphasize the convergence of the line in the image for you to use that as a cue for 3D. Very rarely, unless, like from my perspective, from this standpoint, if I look at that table, the parallel lines of the edges of the table are almost parallel on my retina. To have this kind of convergence on the retina, I have to look at the table from a very grazing angle, from a very slanted viewpoint, from as if I was looking really very, very close to the object. That almost never happens unless you look at the railroad. This is the classical example. Or if you, so the artists here are overemphasizing the perspective, the convergence of the lines.
Can you show us those lines again?
Well, for this building here, this would be this line, this line, this line, this line. All of these are parallel in space and converging to one single point, the vanishing point in the image. And this is exaggerated in this painting for you to have a great sense of this canal.
And the vanishing point here would be, I never understood that vanishing point. And you
this is, yeah, so there are different, okay, the vanishing point is the point where all of these lines that are parallel in space converging. So there's one here, and it should be common to all of these buildings that are parallel in space. And this vanishing point, in theory, should drive your gaze to that particular location. Especially in what is called one-point perspective, when you actually do have the vanishing point visible in the image. They were, especially during the Renaissance, a whole tradition to try to put that particular vanishing point, that is the point where all these parallel lines in space converge in the image, to put that vanishing point right where, at the most important point of the canvas. So where the Christ is going to be, if you have a picture of the Christ, or where the center of the action of the piece is about. Because your drive is ultimately driven there. And even if you look at eye movements, then very likely you're going to make an eye movement towards that location. So in this particular case, I make an eye movement from your first fixation in any image is in the center of the image, of course. And from that perspective, you're going to make an eye movement there. So you are going to make a saccade from here to there. And that might give you a sense of flow from left to right about in this particular painting. And that might help to to give you a sense of depth. This is just perspective.
But this is a convention in painting. There's no such thing as a vanishing point when I'm just looking out on the street.
Oh yes, there is.
There's always a vanishing point.
Yes, but usually that finishing point is where you're heading to. So linear perspective is actually kind of useful and could create some, again, violations when you, some expectations that could be violated. This is a very nice example from Roger Shepard, where the two tabletops here are actually exactly identical on your retina. So I don't have the illustration here, but if I were to cut this and move it here, this is the same as that. And this is the same as that. That's, I think you would agree that the one on the left looks more narrow and stretched than the one on the right. And that's coming from we're using your expectation which you have about this linear perspective in this particular context.
Can you see if that would fit on you? See if that would match the
yeah.
thing.
Oh, did you bring it on purpose?
And so I talked about different cues, and it's at the end of the day, the visual system has to try to match all of these cues together and try to match all the expectations that it has about the world together. This is a nice illustration from Richard Gregory, looking at a concave mask. So in this case, there is a conflict between two expectations. One expectation is that light is coming from above. That's what I mentioned briefly before. And a second expectation is that the face is usually convex. And given that I'm looking at a concave face with a light from above, I can interpret that either as it is as a concave face lit from above, or inversely, I can have exactly the same image with a convex face lit from below. So now I have to choose between a violation of one of the two expectations that I have, either about the light that's coming from above my head, or about the convexity of the face. And in this case, convexity is much stronger, and you see a convex face lit from below. So you are happy to discard your expectation of illumination to preserve only expectation about the face. So-called Ames rule that you might have seen in some exhibitions, where you have a rule that is actually trapezoidal. So it's violating your expectation that you have about the rectangularity of the world out there. And from the linear perspective, linked to this expectation about the different colors of the kind of rooms that you should experience, there is a violation of the expected size of these people. So in this case, you're happy to disregard the expected size for preserving the information coming from the linear perspective and the expectation about the kind of natural statistical environment that you're used to live in. So that's all.
Thank you, Pascal. That was very thorough and very helpful understanding of all the cues of 3D. Great, great. Yes. And Patrick.
And Pascal showed you some of the cues that you would like to sample, because they're the more informative cues that tell you, give you good information on the structure of the things you're looking at. So what I will do is...
Show how wrong we are.
No.
I like your title.
Yeah, is take a look at what artists do and filmmakers do, and that are going to help us understand which of the cues, which of the rules that Pascal was talking about are actually used because the physical world is full of all sorts of rules of physics and optics. But in fact, you don't have to copy all those rules. You don't have to be a slave to physics for it to look really convincing. So you can imagine breaking rules in film like the Bugs Bunny running off the edge of a cliff and not falling. But those are violations of rules that we quickly see, and of course that was the purpose of doing it. But we're after here the subtle rules, equally important rules, that artists can break, or filmmakers can break, that you don't notice. Why is that important? Well, that's important if you are creating some image or film. So you say, well, I don't have to follow that rule. I don't have to make this really absolutely physically possible. Nobody's going to notice. You can get away with things. You saw nice examples from Kevin that you don't actually have to have the people wearing the same clothes from one cut to the next cut. People just aren't going to notice that. So that, yes, you do have continuity editors in the film room somewhere. In fact, they don't really count much because stuff can change between edits and very few people notice. So there are, I understand, websites where people collect all these things. Okay, I had a thing. So I'll try and cover a number of things, but quickly. Now you can find out, so our purpose, different perhaps from your purpose, our purpose is to understand how the brain works and how this really comes about that we experience the world. And there's many ways you could do that. You can actually open up the brain, stick in wires, and measure things, record things, find out what those neurons, the 100 billion of them, what they're up to. So a lot of people do that, you know, it's a pointer, and find it individual cells. So you know the visual part of the brain is about the back third of the brain, which is a lot, which explains a bit about why it's so easy. You open your eyes and you just see stuff. It doesn't seem to be hard, not hard like doing tests or writing papers. In fact, the visual part of the brain is really very intelligent on its own, probably as intelligent as many other animals around us. And it has a lot of inference and computation power. But it starts with just measurements of the world. So what's the color, what's the angle, what's the motion. And some recent work by, Christoph Koch and others, I found that a little further on in the brain are cells that are really, really, really specialized. So it's not just that these measure colors and so on, but some cells are as specialized as responding to individual people. So this is a cell in a person who had electrodes in his brain because he had epilepsy and they were planning a surgery. You have to know what part of the brain is affected or not. And while they're testing these areas of the brain, some psychologists come in and show pictures to find out what's going on in that part of the brain. And they did discover some cells, this one in particular, responded to Jennifer Aniston. Another cell responded to Halle Berry. Another one to Bill Clinton. So the two individuals that this person was familiar with didn't like Jennifer Aniston when she was with her boyfriend at the time. Didn't respond much. These little peaks are the response of the cell to, I think this is So there's some very interesting information you can get by actually recording inside the brain. There's other things you can get by recording outside the brain, imaging things. You can do lots of stuff. What I do in our lab is, I'll just show you one quick example, is I try and study attention, and students and I do all sorts of interesting experiments, of course. And one thing we're interested in is how attention is predictive, that if something is moving, you actually can predict where it's going to be. And in fact, your perception of that moving thing is moved ahead to not where it is, but where it will be in a moment. Here's an example of that. So there's some vertical lines that are red and green, but I'm going to put some motion behind them. Lines are still vertical. Thank you. They're still vertical, but your brain can predict that it ought to be moving, and will make you see them ahead of where they are in the direction of that motion. So of course they never move, they're always vertical and parallel. And you see it most strongly in the middle, but you see it if you're looking here. Of course I get rid of the motion and you see them again vertical and parallel. As soon as it starts moving,
they're not moving.
They actually don't move, they just flash, but the brain thinks they're moving, so it gets prepared for seeing them where they should be. And it's actually so that you can act on them. You're seeing them where they would be if you landed on them. Okay, I won't tell you more about that, but that's a bit what we do to try to understand what's going on in the brain. What I do want to tell you about is how artists get away with stuff. And we haven't really looked at many examples from cinema, but there's tons of them, and they would be as interesting a set of observations as we have here from art across the ages. And the point is that art's really not just art. Of course, for the artist it's art. But for us, it's a huge source of information. It's a bunch of experiments on vision. And it's 40,000 years of experiments, so that's pretty cool. Like I say, what we want to find is the errors that artists get away with. So you look at it and you're not even realizing it's not physically possible. You're not interested in the errors that are obviously deliberate errors or deliberate distortions. We want ones that are non-realistic, not possible, that you don't notice. So you have to have a bit of training to see how to do that. These are shortcuts, so it's clear in a lot of paintings that there are shortcuts. And they're shortcuts that work because these are rules, the visual system that the brain doesn't care about, doesn't check. So it'd be too difficult to check, expensive or whatever. So we get some free science. So this is saying there's lots of stuff that you see all around you all the time, and you just take for granted, and you think nothing about it. Like cartoons, line drawing cartoons. You don't ask, well, why does that work? So this is the point. If you ask, well, why does that work? You might come up with interesting answers. So line drawings are unusual because there are no lines in the world. There's no lines around anyone here. And yet you could be a sketch artist and draw a sketch of everybody here, and I'd look at that and say, oh yeah, that's them. And yet there's no way that you could have ever learned how that works. It's just something that works, and we can show that it's something, part of the physiology is kind of a trapdoor. It's a design flaw that, in fact, artists are able to use to their advantage and make sketches rather than having to create something photographic. But not perspective. So, in fact, the reason why perspective is really boring in paintings is because it's real. So you would only want to look at paintings for stuff you can discover there that you couldn't discover by looking at the world. So I'm looking at this room, and it's in perspective. The lines converge. I think you can see that they're going in the other direction. Yeah, they don't converge down there for you. They converge this way for you. So I don't have to look in paintings for that. I mean, it's interesting that artists figured that out. Right, so what?